Okay, and we're live again. Hello, everyone. I hope you can hear me. If you can hear me, as usual, give me a thumbs up so I can verify that you're actually listening, or rather, so I can verify that sound is coming through, because that is, of course, the thing that well, I want to make sure is the case. So thank you. So today, the last section in chapter 8, and so the last section in the material that will be on the midterm next week. We're going to talk about the continuation of potential energy, and in particular, we're going to talk about how to turn that into potential energy diagrams and use that to determine some things about stability and equilibriums. And we're also going to talk a little bit about sources of energy, which is also typically going to be potential energy rather than kinetic energy. So let's start with, what did I have as a slide? Okay, so we last time we talked about the pendulum, right? It's so someone is asking if there's no homework next week. Well, why would there not be homework? There will be homework on Monday and Wednesday and Friday. They're just small problems, so I don't think it should interfere much, and it will be useful for you to think about the homework problems in regards to the material that we will cover next week. So no, there will be just regular homework assignments, but those should not take all that much time. Maybe not, we'll see. Maybe not due on Friday, but okay, back to the pendulum here. So when we had a pendulum that we released from the starting position at 30 degrees, at an angle of 30 degrees, we released the pendulum, the particle with this mass m, from rest. What would happen is, or what happens is that this particle swings downwards, and the potential energy it has at the starting point is converted into kinetic energy, and at the lowest point here it will have the lowest amount of potential energy, and the highest amount of kinetic energy, and then we'll go back up on the other side, and it will have a larger amount of potential energy again, and it will decrease in its kinetic energy. So the way we displayed that visually is that at these different times, so this is at the starting point, this is halfway between the starting point and the lowest point, and at the lowest point there's a total mechanical energy that consists of potential energy U and kinetic energy K. And we start at rest, so the kinetic energy is 0 here. Halfway between the point where we release the mass and the lowest point, the kinetic energy and the potential energy will be approximately equal. And at the lowest point, there will be a minimum in potential energy, which we've defined to be 0 here in our choice of where we put the reference potential energy, and everything will be in the form of kinetic energy. So we have this kind of constant sum of potential and kinetic energy. That's the total energy, the total mechanical energy in the system. We looked at that similarly in this problem, where we had an object that falls from a helicopter. So it falls from a certain height. It starts off with 0 kinetic energy. It starts off at rest. It accelerates, so the kinetic energy increases. The potential energy decreases as it goes down. The difference in this case was that there was also a dissipative force. So there's some drag, there's some friction with the air, which reduces the total amount of mechanical energy. Now we want to take these diagrams and turn them into a more universally applicable way of thinking about these problems. And to do that, we're going to introduce these so-called potential energy diagrams. And in particular, let's think about this last free fall problem here, but let's ignore any effects of drag. So is free fall in a vacuum or free fall when there's no drag? So the total energy is going to be constant. The total mechanical energy is constant for any height that the object is at. So what we get then is this kind of diagram, where as a function of the height, y, the height above the ground, we can plot the potential energy. And the potential energy is m times g times y. So this is going to be a straight line with a slope that is given by m times g. If the mass is at, or if the object is at a height ya, then the potential energy will be the amount of energy given on this graph by the curve. It will be mg times ya. We can also draw a horizontal line here. That's the total energy, the total mechanical energy available to the mass as it's falling. Or any, it doesn't even have to fall. It can be something that you throw up in the air. So that's the total amount of energy that's available. So a couple of things are immediately visible. There's a point here where the total mass, the total energy is equal to the potential energy. When the total energy is equal to the potential energy, that means the kinetic energy will have to be 0. If E is equal to K plus U, and E is equal to U, then K will have to be 0. At any other time, the distance, or the part of the curve that is above the potential energy line, that is above the potential energy line until the constant line of total energy, that will be representative of the kinetic energy. So we can see that at this point A here, the kinetic energy is displayed above the line, the potential energy is below the line. If we were at y0 equal to 0, everything would be, the total energy would be kinetic energy. If we're at a height y max, the total energy is equal to only potential energy, and there's no kinetic energy, which is, of course, why this is the maximum height. We can't get above that height because we don't have kinetic energy. And now we can think about this in diagrams in terms of the time evolution of a system. So we can use this to for example, describe free fall. We can think of the particle starting here at y max. So what will happen? It will start with a high potential energy, 0 kinetic energy. Let's say it falls to a height of ya. What will be the speed of this particle? Well, we'll be able to determine the kinetic energy, and from that we determine the speed. Let's say we start at y equals 0, and we throw up the particle with a kinetic energy that gives us the total energy. And we're starting at a potential energy that's equal to 0. So that will give us, that initial kinetic energy will give us the total energy line, and we can use that to now calculate what the maximum height is that we will be able to reach. For example, if we throw a mass up with a certain potential, with a certain kinetic energy, with a certain initial velocity, what will be the maximum height that we'll be able to reach? Of course, the thing that's relevant here is then going to be the vertical kinetic energy, right? So that's an example of a potential energy diagram. So we just plot the potential energy versus the position of the that is relevant in the potential energy. So in this case, that's going to be the height. The other example where we encounter this potential energy diagrams would be similar to the pendulum, but in this case it's going to be a different implementation of a pendulum. It's essentially a glider on an air track that's moving between two springs. So it's the same thing, really. It's there's a, if we push the glider to the left, there will be a restoring force because one spring will push it back and the other spring will pull it back. So there's a restoring force that pulls it back to the center. If we pull the glider to the right, there will be a restoring force that will try to bring it back to the left. We can write down the potential energy of this system because we have two springs here. We can write it down as 1/2 times k times x squared. So it's going to look like a parabola. So this is the potential energy as a function of the x position, the displacement from the equilibrium. And again, we can add a line, a horizontal line for the total mechanical energy, the sum of kinetic and potential energy. And that will give us, for any position that the glider might be at, it will give us the potential energy, it will give us the kinetic energy as the other component that we need to make up the total energy. And we can derive some conclusions from this graph. For example, we can determine the maximum positions on the right and on the left that this glider will be able to reach. It will be given by the positions where the potential energy is equal to the total energy, the total mechanical energy. And we'll see, based on the fact that this is a symmetric curve, we'll see, of course, that x max on the left will be equal in magnitude to x max on the right. We can derive some other information from this. For example, what happens if our total energy is less? What if it's, for example, half this? Well, if it's half this, we'll be able to determine where the new x max is. And just from this graph, we'll be able to read off that x max for a total energy that's only half as large, x max will not be half the original x max. It will actually be 1 over square root of 2. So it will be a different factor than 2. But on this graph, we can immediately derive that conclusion without even having to do any math. The important points that are indicated here are these so-called turning points. So if we have something that is moving on this potential, in this potential energy, there will be 2 turning points, which is when the object that moves along x, when the glider moves in x towards x max, it will at some point reach this point where the kinetic energy will become 0, and that's when it will turn around and start moving in the other direction until it reaches the turning point on the other side, and it starts moving in the opposite direction, and so on, back and forth and back and forth. So those are the turning points. That's where the total energy is equal to the potential energy, where the total energy curve, or the total energy horizontal line, crosses the potential energy curve. The other point here is the equilibrium point. Because remember what we talked about, that the first derivative of the potential energy to the position, or to the variable that it depends on, is going to be the force. So the slope of this curve is going to be the force that the glider in this case experiences. So in this case, where this tangential line is indicated, the total force will be the derivative is negative, so the total force, it's actually minus the derivative of the potential energy, so that will be a force that goes in the positive direction. At this point, the equilibrium point, the total derivative is 0, derivative of the potential energy to x is 0, so the force will be 0. So this is our equilibrium point. And the nice thing is that we can apply this to any problem where we are given a potential energy, even if solving an equation for E equals K times U leads to very complicated math. In some cases, even when there's potential energies that you would not be able to solve algebraically. So one example would be this, for example. This is a potential energy that now has a 4th order term and a 2nd order term. So it's a 4th order curve that describes the behavior at large x, and then there's a 2nd order parabola term that describes the behavior at small x. And the reason why I can say that the large x values will be more important in the higher powers if the values for x are small, then the larger powers of x will go to 0 more quickly, and so the ones that go less quickly to 0 are going to be describing the behavior around 0, and that's going to be this minus x squared, or minus 2 times x squared term, which will give us an inverted parabola. So in this case, opposite to the x squared behavior in the previous energy diagram. In this case, it's a minus x squared, so it's an inverted parabola. So what happens now if we have a total energy that's equal to minus 0.25? So we can identify turning points. There's minus r and minus p, which are turning points. That's where the total energy line intersects with the potential energy curve. So minus r minus p. There's two other turning points, p and r. And what we know is that the particle, when it reaches the turning point, it will turn around and go back, right? So in this case, the only place where, or there's two distinct parts of the x position that this particle can move. It can move between minus r and minus p, and it will move back and forth between those two. Or it can move between p and r, right? It cannot be between minus p and p, not with that energy, and it cannot be outside of, it cannot be at a position x greater than r, or at a position x less than minus r. Those are not allowed for that energy. If I were to, for some reason, if I positioned this particle at, let's say, between the origin and p, I would have to give it a higher potential energy, and therefore I would have to give it a higher total energy than minus 0.25. And then, of course, if I give it a higher total energy, then this curve would actually be higher up here. Let's say it would be at minus 0.1, and so our turning points would be further apart. So we'd have p here and r over here, and the motion of the particle would be a larger range of x, but the same conclusions would still be valid, that we'd have two separate regions in which the particle can move. Only when the energy becomes larger than 0, only when the energy is larger than 0 is there a single region in which the particle can move. Because then the turning points are going to be only the turning points represented by r here. There's not going to be any turning points p, because there's no intersection between the horizontal line for a total energy greater than 0 and the potential energy curve. So Julian is asking, what motion would this diagram represent? Well, this is actually, this could be a very, I mean, there are examples of motion that that is described by this. I would have to, you probably have to come up with something that is beyond the mechanics examples that we've covered in this course, but certainly in the case of electrical systems, electric charges or magnetic fields, it would be easy to come up with a situation like this. So in case you want an example, and sort of looking forward a little bit to a future term, actually, let's say we have our x-axis here, and we have an electric charge here and an electric charge here. Let's call these both positive electric charges, and I'm moving, and let's put a negative electric charge here and a negative electric charge here. So the only thing you need to know is that positive and negative electric charges attract, and opposite and positive charges repel each other. Likewise, like charges repel each other, and opposite charges repel each other. So if I now take a positive charge that I allow to move along this line, in the center here, it won't like to be there because it will be attracted by the -1 and the -1 here, and it will be repelled by the plus charges here. So we'll end up with a higher potential energy in the central region. The particle will want to move to the negative charges. If we're beyond this negative charge, the particle will want to come back because it's going to be attracted. So we're going to end up with a potential energy that kind of looks like this, with the minimum where those negative charges are, the maximum right at the center line between those two plus charges, and there's going to be some details that that make this not exactly look like the quadratic and the quartic term, but you get the idea that this is the kind of diagrams that you would be able to draw. And so now choosing the kinetic energy or choosing the total energy allows you to pick a particle that will have enough energy to kind of bounce around like this, or you can give a particle less energy, less kinetic energy, and it will be stuck in one of these valleys in the potential energy. So I don't want to dwell too much on this example with the charges. That's going to be a topic in the next part of this course, as in 2152 or whichever 1070, whichever course you're taking, that will treat the electrical systems and electric charges. But these are the kind of potential energies that are very common in physical systems. Ultimately, what we will also see is that if you only look at a narrow enough region around an equilibrium, which is something that we are very commonly allowed to do, if you're looking at a very narrow region around the equilibrium, everything will always look like this. So we like to say that if you look at something around an equilibrium, by definition, around the equilibrium, you're at the minimum in the curve. So in the potential energy, the first derivative will be 0 at the equilibrium. So what's the only derivative you can have then? Or what's the next derivative you can have? It's the second derivative. So if you have a potential energy that only has a non-zero second derivative, what you have is a quadratic potential energy like the one for the spring. So this is pretty much the most important potential energy diagram that that you will encounter, because it essentially represents every single system as long as the motion around the equilibrium is small. And fortunately, it is a very commonly applicable situation that the motion around equilibriums is small. As soon as we are talking about motion around equilibrium that is large, then usually we're not in stable systems, and there's a whole lot of other things you have to worry about. But for anything that is stable in nature, you will be moving around an equilibrium, and so this quadratic potential energy is going to describe that. So that's why this kind of potential energy is going to come back. I don't even want to say it's going to come back very often, because that would be an understatement. It is going to come back every single day of a physicist's life. The potential energy that depends on x squared, for x, some kind of variable, is going to be very common. Okay, so actually let's look at that in a little bit more detail, even mathematically. So let's say we have a potential energy, and we know the potential energy as a functional form. So let's say we have, let me move this away. So let's go from potential energy, u as a function of x, to x as a function of time. Because ultimately that's what we're after, right? We want to go from our potential energy distribution, from our potential energy function, to how does our particle move as a function of time. So let's see, how would we solve this? So let's start from the thing we know, right? The total energy is the kinetic energy plus the potential energy. So in this case, that will mean this is 1/2 mv v squared plus u as a function of x. And so really what we're saying here, that the constant energy, we can say E0, is equal to 1/2 m dx dt, which is a function of time, squared plus u of x as a function of time. So we can solve this for dx dt. Let's solve this for dx dt. So v, or in other words, solving it for v, we can write first 1/2 mv squared is the energy, the total energy. I'm not going to write the subscript 0. Just remember that the energy is constant here. So E minus U of x. So V is going to be 2 times E minus U of x over m with a square root. And that's equal to, or dx dt, or derivative, right? So you might say, well, if this is dx dt, then I can take the integral. So I get x as a function of time, which will be the integral of 2e minus u of x over m with a square root dt, right? I can do that integral from t0 to a time t, and that will give me my x as a function of t. So that's the first attempt we can try to use to determine the position as a function of time, starting from the potential energy. Now, there's a problem with this, of course. We can't do this integral until we know what x as a function of t is. We can't calculate this integral because there's still an x in that integral. So this isn't actually going to work. So that's not the way we can calculate that integral. So instead, what we're going to do is we're going to take this and we're going to turn this on its head. dt dx is m over 2 e minus u of x with a square root. And then what we're going to do is write this now as dt is m over 2e minus u of x with a square root dx. And now we can take the integral. We can take the integral of dt between t0 and t. We can take the integral here between x0 and x, so the initial time and the initial position, so our initial conditions. And so t minus t0, which is this integral here, will be the integral from x0 to x of m over 2e minus u of x with a square root dx. And now this is an integral we can actually solve, because we have the thing that depends on x that we're integrating over x. I'm not saying this is an easy integral, right? You can sort of see that I mean, for those of you who are only now starting to cover integrals, this is certainly not an easy integral. But even in the general case, this is not an easy integral. Fortunately, again, u of x, that is 1/2 kx squared, is the most common potential energy that we're going to encounter. And for this potential energy, we can write t minus t0 is the integral from x0 to x of m over 2e minus 1/2 kx squared with our big square root dx. And this turns out to be a solvable integral. Those of you who are familiar with integrals will recognize the integral of d. Let's see, what is it? I guess I'll just write it as dx of 1 minus x squared, which is the inverse sine of x. Or in other words, the derivative of the inverse sine is 1 over 1 minus x squared. And that's what we get here. We have a constants, we have an x squared over here, we have a square root with some other constants thrown in. So that allows us to solve that integral. And what we'll find is that that integral, after a little bit of algebra and introducing some other variables and so on, you'll find that this is m over k inverse sine of x over 2e over k with a square root evaluated between x0 and x. And that we can invert. So if we're looking for just the solution for x, we can invert this. And if we assume that x0 is 0 at t0, then we'll find that x as a function of time is 2e over k times the sine of square root of k over m t minus t0. And what does this tell us? This tells us now that the position for a potential energy that is quadratic, that is 1/2 kx squared, the position will vary with the time as a sine of that time since the original time. And that will, of course, as a function of time, it will look like this, x of t. So we'll end up with our sine curve around the minimum around x equals 0. So what will happen is we'll just end up with our particle moving back and forth. And what will be the maximum x max here? It will be when the energy is equal to the total potential energy. So it will be exactly when we have an x max that is equal to this 2 times the energy over k with the square root. But this would work, this approach, even if you have to do the integral numerically, will allow you to determine the behavior of, or the time behavior starting from the potential energy. So the reason why I'm going through this is not to make your brain hurt, right? The reason why I'm going through this is to indicate that there's really everything you need to know is in these potential energy diagrams. With this potential energy diagram, it is just a matter of solving a simple, or maybe not so simple, integral to get from the potential energy to the behavior of the system, the time behavior of the system. So it really describes what we would call the dynamics of the system. It describes how a system behaves from a starting time and how it moves around in its parameter space. So that's really a fundamental approach here. Okay. So yeah, read this in the textbook. It goes over it in a little bit of a format where you can actually rewind and then look at it again. Well, maybe these YouTube videos actually allow that too. But it presents it in a slightly different way as how I've presented it here. Not all that different actually, but reading it in their words is probably going to to give it a little bit more clarity as well. There's no need that you would need to be able to do this derivation or any kind of integrals for the midterm, so you should be fine there. Okay, for the last bit of this section, we're gonna look at a slightly higher level topic, and that is the sources of energy. So sources of energy is sort of the last section of the chapter, and what we're talking about when we talk about sources of energy is the different forms in which we can have energy. We already know essentially two forms, right? And that's essentially the two forms that there are. There's kinetic energy and there's potential energy. But of course, you think of sources of energy also as radiant energy from the sun, as nuclear energy that is used in nuclear fusion or fission even, chemical energy that's in your food, electrical energy that's for example in this case making your laptop go. So in many cases, those are actually just specific forms of kinetic or potential energy. Let's start with the one here, thermal energy. That's essentially kinetic energy. Thermal energy is the kinetic energy of atoms and molecules, or in this case, it's actually the kinetic energy of the wind hitting the turbine blades here. Electrical energy, where is it here at the bottom? So this is the potential energy of the potential energy of electric charges that I actually use in the aside there. The electric energy, the potential energy of charges in electric fields, or it is the kinetic energy of charges that are moving with a velocity. Chemical energy is often, again, potential energy of electric charges in fields. Radiant energy is the potential energy that is in the electric fields. So all of it is really, ultimately, we can reduce it back to potential energy and kinetic energy. One thing that you might have heard about this is there's ways that people can actually store large amounts of energy by pumping water from a lower reservoir to a higher reservoir, only to have it then flow back from the high reservoir to the low reservoir through a hydropower plant. Essentially, it's a gravitational battery. And that kind of gravitational battery is a pure example of the kind of potential energy that we've seen, right? That's the energy that higher reservoir has is potential energy compared to the water being in the lower reservoir. And the amount of energy is actually m times g times h. So that, of course, is an example which makes it very clear that there is potential energy. So in the case, maybe I should make a drawing. Oops, where am I here? There we go. So gravitational potential energy. So that's when we have a reservoir here and a reservoir here, and typically, obviously this is on the side of the hill, and we have a hydropower plant that allows to either pump water up and expend energy, or that allows the water to flow down. And this, I should draw this vertically, the height h gives us a potential energy that's equal to m times g times h, where m is, of course, 1 million liters of water. So obviously m will be large, so that will make that potential energy large, but allows us to store large amounts of energy for future use. And then finally, the last two concepts that the textbook talks about is the difference between renewable and non-renewable energy. And I don't think I need to explain to you what renewable and non-renewable energy is. So the difference is, of course, that one of the sources, the non-renewable energy, which is, of course, unfortunately still the largest amount of energy, or the largest fraction of the sources of energy that is consumed. That is energy that is not replenished within the lifetime of the use of this energy. So that's fossil fuels, includes nuclear, whereas renewable energy uses sources of energy that actually are replenished within a useful lifetime of the energy source. So this is, for example, solar power, where there's always more solar power arriving. There's or always more sunlight and radiant energy from sunlight that is arriving. Wind energy, there's always more wind that we can use. We're never going to use up all of the wind, so that allows us, those are the renewable sources. So that's it for this chapter 8. Yeah, biomass is also, well, biomass we technically, I guess that's maybe a little bit on the on the borderline between renewable and non-renewable. So the midterm will cover everything through this chapter and this section. And what we'll start with next week is going to be linear momentum. So that's going to be collisions and so on. So, and that's it for today. So have a good weekend, and I will see you on Monday.